Right, we're going to try this salt prep worksheet. It's a bit tricky. So basically we need to find out whether salts are soluble, insoluble. Yeah, they will leave a precipitate, and there you'll have to what do you call it? Evaporate off some water till it reaches point of crystallization. And then you've got sodium, potassium, and ammonium salt. These are going to be done by titration. Right, let's crack on. Barium carbonate. Barium carbonate is an insoluble compound. It is formed as a precipitate. So look, I think they've given us a clue: insoluble and precipitate. So we know when to work from. Yeah, when solutions of soluble compounds, barium chloride and sodium carbonate, are mixed. When the solutions of the soluble compounds are mixed, no precipitate form. So this is then a soluble. That is insoluble. This is soluble. Complete the table to show the results of mixing some compounds. So basically, you've got to know. Right, let me just go try to figure that one out and get a summary. Right, here you've got the summary. So, right, let's just look at this and then we can. Right, so if you look here, there, all ammonium, potassium, and sodium, I can draw a straight line, salts are soluble. All nitrates are soluble. Right, you can then, all chlorides are soluble except lead and silver. Same thing with sulfates, lead and silver, and then you add barium and calcium. And then carbonates and hydroxides except barium. This is a tough one to do. Let's try to see if we can picture it in a better way. Let's get rid of that. What if you did this in your head? Yeah. So all these are soluble. There you go. All these are soluble. There you go. These are all soluble. So ammonium, potassium, sodium, all nitrates, chlorides and sulfates except lead, silver. Let's do that. Except lead, silver, and barium and calcium. and there's one hydroxide that is not soluble, that is, sorry, that's outside that range, is, you could learn it in reverse, but that's what we need to know basically. Right, so if you add barium chloride, if you add barium chloride to sodium carbonate, you end up with barium carbonate. If you add barium chloride to sodium sulfate, you're going to end up with barium sulfate, and it's going to be a precipitate. Right, potassium chloride with sodium carbonate, you're going to get no precipitate. Calcium chloride with sodium sulfate, you're going to get a precipitate. Calcium sulfate precipitate. You can put precipitate of calcium sulfate or calcium sulfate precipitate, it doesn't matter. Right, the equation reaction. When solutions of lead 2 nitrate and potassium bromide are mixed, a precipitate forms of lead bromide. So lead bromide is a precipitate, so we know it's a solid. When solutions, that's going to be aqueous and aqueous because it involves water. They're going to be aqueous solutions. And a solution of, you're going to get an aqueous solution. So I suppose that's how you can pick it out. So the clue is in the question. Right, in order to prepare a pure dry sample of lead bromide, the student took the mixture and then filtered it, washed it with distilled water, and then left in a warm place to dry. So in this case, why did the student filter the mixture? Because the student wanted the precipitate of lead to bromide precipitate or residue or solid. Lead bromide precipitate. Okay. Why did he wash the solid residue? So this is again a standard answer to remove or to wash away any impurities, or in this case it will be, the impurity was potassium nitrate. Why is it better to use distilled water rather than tap water? Okay, again it'll be a standard answer. Distilled water does not contain any impurities. Why did he leave the solid in a warm place? Right, to remove or evaporate off the water, or to make it evaporate off quicker. Right, you know, this here is a good definition of soluble salt. That is worth noting there. Right, so let's take a shot of that. No, not yet. So it's worth taking a shot of this and storing it. Right, okay. Copper sulfate. The salt made was copper sulfate. Should we just right? Let's go through this. Copper. Soluble salts can be made by reacting acid with metal hydroxide, metal oxide, or a metal carbonate. Insoluble salts can be made by reacting, using a precipitation reaction. That's when you'd react two solutions, and what would happen is you'd get a precipitate, and then that's the one that you filter off, wash, and leave in a warm place to dry. So now we need to complete these. Right, copper sulfate. If I want to use an acid, it'll be sulfuric acid. Right, can you see that hydrochloric acid gives silver chloride? What do you think that acid will be? Nitric acid. Okay, metal compound, copper oxide. Right, I want silver chloride, so I'll have to use silver nitrate as a compound, potassium carbonate. Right, it's a sulfate, so it will be solid. Just bear with me 1 second. Okay. So let's. I should have just left it there. Right. Okay. So you've got potassium. You're gonna end up with potassium carbonate. So carbonate and potassium. So all potassiums are right. Okay. This here. Right. Okay. I've misread that. I was looking for that. We don't need that. Let's get rid of you. Put you to the side. That's not good. Right. So what they're asking for is copper oxide is a solid, a black solid. Silver nitrate is an aqueous solution. Potassium carbonate can be either aqueous solution or solid. So we'll just put aqueous solution. It can come in many forms actually. So they'll accept any. They'll accept solid or even solution. An acid is a source of hydrogen ions. Write an equation to show the ions when sulfuric acid is dissolved in water. So we know it's H2SO4. Right, show that the ions formed. So you're going to end up with SO4 2 minus, SO4 2 minus, yeah. And you've got H plus ions, and you've got two of those. So the charge is there, so you've got two pluses and you've got one set of two minuses, so they balance out. Okay, that's it. There's nothing else that they want from that, which is fair enough. Right, we need to now prepare. It's a 5 marker. We need to now prepare insoluble salt. So they've said solid nitrate and solid sodium chloride. So they've given us everything that we need to know. Right, step 1. because they've said they've given you solid and solid, so we need to dissolve lead to nitrate and sodium chloride in water. Mix the solutions in a beaker using glass rod. Always add experimental details. You're gonna then get an insoluble, look, you're gonna get an insoluble salt. Then you filter off the precipitate, so get rid of the liquid part, the solution, and then what you do is wash off residue, wash off residue with distilled water or deionized water. Distilled, I like to use the word distilled, it's stuck in my head. Right, and then you leave in a warm place to dry, or tap off with a you can tap off with a paper towel. Okay, that's all your marks done. It's as simple as that. This one had all the information in the question, which is good. Right, some pieces of apparatus used to measure volume. So that there is a burette. Okay, they've not. Right, let's have a look. Burette. It's burette. Burette. I can't spell burette. Right, let's get rid of that. That's no good, is it? I can't spell that. Burette. That is a pipette. This is a beaker, a graduated beaker, and this is a measuring cylinder. Okay. So we're gonna find the concentration of sodium hydroxide solution. So obtain about 150 centimeter cubed of each solution. Using the measuring cylinder to exactly add 25 centimeter cubed of sodium hydroxide into a conical flask. So let me try to go through that. So I've added 25 centimeter cubed of sodium hydroxide. Right, we're going to add a few drops of universal indicator. Then we're going to add using the burette. We're going to add sulfuric acid. Okay, so until that's neutralized. So it's gonna go from red, green, and blue. So it's gonna go from blue to green. Give the name of the most suitable apparatus for step 1. About, it's in about. So we could use a beaker because it's roughly what we want, yeah? Give the name of the piece of apparatus in the diagram that should be used instead of measuring a measuring cylinder in step 2. Instead of measuring cylinder, right, a pipette. And I think the reason for that is, if you notice here, it's got a fixed volume and it's got a mark there. It's going to be a bit more accurate because it's thinner, so you're going to lose less. You're going to leave less on the sides, and you can transfer it more accurately. I think that's the idea. Why is the universal indicator not a good choice? Again, this is a standard question, right? The color change is gradual, yeah, and not sharp, or you can say, or is not sharp. Right, what would you say? You can say there's 2 methyl orange or phenol phenolphthalein, phenolphthalein. I remember it as phthah, so I can spell it. Well, try to spell it. So you can use any one of these two. They've got a sharp. This has got red, orange, yellow, colorless, pink. Because that's how we remember it, don't we? So this is acid, this is neutral, and this is alkali or base. Right, why is a pipette not suitable for adding acid in step 4? Right, because it delivers a fixed amount. It has a fixed amount of liquid, right? Or you can say you cannot control the amount you add with it here, yeah? Okay. So you can't control you can't control the amount you add. It's harder to control it, that's what they say. Right, these cause me a lot of headache because I end up misreading these. Right, let's have a look. Right, okay, so that there is 3, that there is 2, 2.1, 2.2, 2.3, 2.4, 2.5, 2.6, 2.7, 2.8. So it's between the two. Right, so before would be 2. So that there is 2.7, that there is 2.8, and it's in between, so we can write 2.75. right, and after is, that's 23, that's 22, that there, can you see that's bigger, that one there is bigger, so that's going to be, let me get that right, 22.5, that there is bang on 22.5, 22.6. Right, because they're working to 2 decimal places by the looks of it, we can write that. It does get a bit strange, but 22.60, if you subtract the 2, you get 19.85. So this is just simply on a calculator. Subtract them two to get the volume added. Right. Right, so we're going to repeat the experiment using different concentrations of sodium hydroxide. Right. This is the main one. Now we need to have a look. Let's get this word concordant. It just means concordant. It just means 2 results that are in agreement or close results. What defines a close result? They've said it has to be 0.20 plus or minus. So what you can do is you can get a calculator and check to see which of these is 0.2 from one another, and it'll be these two. Yeah, because that's 25 away. That's 25 away as well. So it's only them two. Right, then what you do, so we've done that, we've ticked the 2 boxes. Then you work out the average. And average is simple, isn't it? You just, these are easy marks that they're giving away to us, really, I think. 23.4 or 23.40. Okay. Right. This is again like a typo, don't worry about that. It's supposed to be an arrow going forward. So potassium hydroxide, sulfuric acid, potassium sulfate, and water. So this is a ores. Well, we remember it as ores, don't we? Ores. So that is, let me get this right. This is alkali plus, so that's alkali. That there is acid. Gives water and salt. Right, then you've got the other one, which is bores. And now this here is the same thing, but it's a base. What did we say the difference between a base and an alkali is? If you can dissolve it in water, if it's soluble in water, it's called an alkali. Right, I think that's about it for that. Quarks. This is what somebody told me. Quarks. This here is carbonate. That's acid again. This is water, salt, and this here is carbon dioxide, and mash. Try to learn these. They're really good. That someone told me those, and very handy. So this is going to be a metal. That again is an acid. That again is salt. And that there is hydrogen. Right, now this comes up a lot, this actually, so just pay attention to this. Carbon dioxide, hydrogen. So what are you going to observe? What are you going to see with your eyes? You're going to see effervescence. This is another name for bubbles or fizzing. So if they ask you what you're going to observe with this sort of reaction, you'll see bubbles, effervescence. Right, now this requires a bit of thought. Volume of potassium hydroxide is that, volume of sulfuric acid is that, concentration of sulfuric acid is 0.05 moles per decimeter cubed. They've added 2 extra zeros to show the accuracy. Right, if you want to work out the number of moles of sulfuric acid, it's moles over 1,000. Right, so they wanted to turn that into decimeter cubed. They should have divided by 1,000 instead of 100, yeah? Divide by 1,000 instead of dividing by 100. Step 2 is amount of sodium hydroxide, 23. Let's go back up. Right, you need 2 sodium hydroxides for every 1. So this is how I remember it, yeah? So you want 2 moles of this for every 1 mole of this. Look, there's a 1 here. It's hidden, yeah? They don't have to write it. So for every one sulfuric acid, I need 2 potassium hydroxides. So it's mole ratio 2 to 1, or in this case it'll be 1 to 2. So what did they do? They divided by 2 when they should have multiplied by 2. Should multiply by 2 instead of dividing by 2. Okay, the last one, concentration. That's how many moles they are. And these two should be right, okay. Let's go back up. Potassium hydroxide, how much did we use? 25.3. Because it's potassium hydroxide, they've used the wrong figure. They should divide by 25 instead of divide by 23.60. Okay. Right, we'll knock that one on the head there. We'll carry on with the next video. Right, that was a tough one.